This talk is really overdue because Justin was supposed to give this talk 2 years ago, and then I guess the pandemic struck, and we ended up delaying, always rescheduling, and eventually now we're here, so that's good. Justin was an undergraduate here at Stanford. In fact, he worked in my group, and he was so kind of involved in his project that after graduating, he took a year off, but instead of relaxing, he continued doing the analysis of the experiment and ended up publishing my only astrophysical journal paper where Justin was actually first author. So that was a very impressive performance. He then went on to graduate school at Berkeley as an NSF fellow and started working on IceCube, which has been one of his activities since. He was here as a Kavli fellow and Einstein fellow as a postdoc. And then he's been assistant professor and associate professor at University of Wisconsin. Let's see. At Wisconsin, he got a number of teaching awards, and also he has something. He has the U.S. Antarctic Service Medal, which I would have thought that something you have to fight to get to this household to actually get that. But apparently, you can actually do that. Also get it for scientific merits, I guess. Finally, I can't resist saying that Justin, I think, cornered Stanford teaching Tibetan. Is that right? That I think so. So he's going to give me talk in Tibetan. This is the first talk in Tibetan that he had. So anyway, thanks a lot for coming. And this is Justin. You should probably put this in your pocket and click this. Maybe I can do it. All right.
All right, thank you, Giorgio. Is the Zoom audio okay? In addition to room audio?
Yes.
All right. Thanks a lot, Giorgio and Stanford, for hosting me. I think it's been a hard 2 years for everyone. It's great to be back in person lots of places, but I think if there's anywhere I'd want to be back in person, it's here at Stanford. It's been great seeing old friends and mentors and making new ones today. I think I took the Physics 60 series here. So a lot of my formative years were in this room and on this campus as an undergrad and then again as a postdoc. And I think, and as Giorgio mentioned, I first got into research, physics beyond the classroom with him, working on a neutrino astronomy project. I think this is also where I first heard of IceCube. I think Francis Halzen gave this colloquium about 20 years ago and I was in the audience. I looked through my old notebooks and I had notebooks from that time, but I couldn't find it from that day. But it's great to be back at Stanford. I'm gonna do a little bit of an experiment today. When I was in high school, this is pre-Giorgio days, in high school I was taking a science class and I was writing a science report for the lab class. And I said, first I did this, and then I did that, and then I did this, and then I did that. And the instructor said, don't tell science chronologically. But I'm gonna violate his guidance, and I'm gonna try to tell a chronological story. So I'm gonna start by introducing the players in the story. So here are a few of them. On Earth, we have the IceCube Neutrino Observatory that you'll hear about. We also have the magic TeV Gamma Ray Observatory up here. In low Earth orbit around the Earth, we have the Fermi Large Area Telescope that has been led by Stanford and SLAC in large part. And then out in space, we have a variety of particle accelerators and other sources of multiple messengers, some of which are electron accelerators or colliders, some of which are large, at least large proton or hadron accelerators, if not necessarily colliders. And we're going to hear about a variety of different sources, including accelerators that play roles in this story. So continuing, and by the way, I know there's a wide variety of backgrounds in the audience, so I'll take questions at the end, but also feel free to jump in along the way. So to continue setting the stage, like many good stories, where and when does this one occur? In a long time ago in a galaxy far, far away. Where exactly? Let's start quantifying that statement. So how long ago? The first player in the story was about 5 billion years ago. How far away was that galaxy? Roughly 5 billion years away as well. And in that galaxy, a very massive star collapsed. We don't know exactly what it formed, maybe a neutron star, maybe a black hole, probably a black hole because it was so massive. It formed a jet of matter and radiation, including really bright gamma rays. It was among the brightest flashes since the Big Bang. And today we know this as GRB 190114C. I'll give the names for the experts or people who are interested in looking them up, but pay attention mostly just to the storyline of who these key players are and the sequence of events in this chronology. So that was 5 billion years ago. And then zooming forward a mere 1 billion years, then 4 billion years ago, another galaxy. So that prior galaxy had the star that collapsed into a black hole, roughly stellar mass black hole. Now this is a much more massive black hole. We now think today that most, if not almost all galaxies have giant black holes at their center from millions to billions of solar masses, including this one. And so 4 billion years ago, this giant black hole at the center of this galaxy emitted a burst of high energy neutrinos. And then a few years later, it emitted another neutrino, at least one neutrino, probably much more, but one that we know of. And at the same time, there was also a burst of gamma rays at that time. And then billions of years later, humans named this object. This is named after a radio telescope in Texas, so it's called Texas 0506 plus 056. Zooming forward another billion years, 3 billion years ago, there was another galaxy. We've got an image of this one. The others were kind of artist illustrations, artist visions. This is an actual image. In this case, 3 billion years ago now, another galaxy emitted a very short blip of radio waves, very, very short. It only lasted about a millisecond. And then it continued doing that on different timescales up to several years. Today we know of this as FRB, fast radio burst 121102. Now zooming forward another couple billion years, 1 billion years ago, 2 small black holes. These are now back to almost stellar mass, but not all the way down, somewhere like 20 to 40 solar masses each. 2 black holes merged. They'd been spiraling around each other for a long time. They eventually finally merged a billion years ago, and they launched a burst of gravitational waves. Now we're zooming forward, no longer on the billion-year time scale. This is, by the way, known as GW 150914. Then zooming forward to only 130 million years ago, now instead of black holes, a pair of neutron stars merged. This is only 130 million years ago. They'd also been spiraling around each other for a while. They eventually finally merged. They emitted a burst of gravitational waves and a flash of light. So we're starting to see the theme that these different sources emit different types of signals that have been traveling across the cosmos ever since. This is known as GW 170817. Zooming forward again in time, now going from billions to millions to only thousands now. Now we're at 170,000 years ago. Another massive star collapsed. This is closer by now, though. This is in our cosmic neighborhood. And it emitted a burst of light again and neutrinos. This time, it produced this burst of neutrinos. This came to be known as supernova 1987A. And it has this interesting ring structure in the optical image. Zooming forward again in time, we come to only 30,000 years ago. This was like that radio blip that was a billion years ago, but now this was only 30,000 years ago. Very similar phenomenon, different energy scales, different distances and time scales. Again, a blip of radio waves, again, only millisecond time scale. And this time, in addition to the radio waves, there was also a burst of X-rays. And that's known as fast radio burst 200428. And the X-ray component is known as soft gamma ray repeater 1935, et cetera. Okay, zooming forward again, we're coming almost up to the present day. 5,000 years ago now, again in our own galaxy, but not as far across it, there was a white dwarf that was accreting material from its companion. That material built up, eventually ignited an explosion. And so there was a bright flash from that white dwarf surface. In addition to the bright flash in the optical that you can see here, this is from the constellation Ophiuchi. There was also a burst of very energetic light, gamma rays, in the GeV band and even all the way up to the TeV scale. And so that's the nova RS Ophiuchi. So these are our players over cosmological and astrophysical timescales over the last billion up to thousands of years in the recent past. And so I'll just briefly recap that before we continue in the recent past. Okay, so 4 billion years ago, a galaxy emitted gamma and neutrino bursts. 3.8 billion years ago, life began on Earth. 1 billion years ago, 2 small black holes merged. 0.5 billion years ago, fish evolved. 0.4 billion years ago, land plants evolved. 0.2 billion years ago, dinosaurs and mammals evolved. So while all these different messengers from all these different signals were racing across the universe, all of this was happening here on Earth. 0.1 billion years ago, the 2 neutron stars merged. Only 300,000 years ago now, Homo sapiens evolved, and that included arguably astronomers. So I think probably as soon as Homo sapiens evolved, they were looking up at the sky and trying to understand it and doing astronomy. Particle physicists had not yet evolved. And then 5,000 years ago, that nearest cosmic object, cosmic phenomenon that I named happened. So that was the explosion on the white dwarf surface. In the meanwhile, all these different things on Earth were evolving, including the humans, including the astronomers, and then particle physicists evolved. So arguably, the ancient Greeks were the first sort of reductionist particle physicists, including Democritus, 2,000 years ago. And then 50 years ago, especially right here at Stanford and SLAC, modern particle physicists evolved using particle accelerators. And they're basically in some ways mimicking processes that we think had been happening in some of those other accelerators, those thousands up to billions of years ago. And so in a way, the humans had been evolving and they'd been racing the clock to try to understand the technology necessary to understand astronomy and particle physics, and then also to build detectors for these signals that had been racing across the cosmos. And luckily, they built these instruments right in time to detect all of those signals that I mentioned. Okay, so you can think of a lot of progress in astronomy and astrophysics as starting with those early astronomers, early Homo sapiens just looking at the sky with their eyes, and they could see less than an octave, less than a factor of 2 in wavelength, from about maybe 3 to 400 up to 700 nanometers. This tiny sliver, only less than a third of an order of magnitude in wavelength. A lot of the progress in astronomy has occurred from increasing those frontiers in both directions, down to much shorter wavelengths through the ultraviolet X-ray into the gamma ray, and out through much longer wavelengths into the microwave and the radio. To keep going beyond the X-ray and the gamma ray, one side note, once I gave a talk to some undergrads and someone asked, what's beyond gamma rays? What's even shorter wavelength than gamma ray? And I said that it's not really fair because there is no name. We just keep calling it gamma rays all the way down, but they can get arbitrarily short wavelengths. So gamma rays span a huge range of the electromagnetic spectrum. But we can also start using other particles. So a lot of the history of astronomy is expanding waveband coverage to do multi-wavelength astronomy. But to get to the very high energies, the very short wavelengths, we're also interested in doing multi-messenger astronomy. So at these very short wavelengths, very large energy scales, we can keep doing gamma rays all the way through TeV, even up to PeV, 10 to the 15 electron volts. But we can also switch to other particles, including neutrinos that I'll tell you about with IceCube, even including charged particles like protons and other hadrons. And so if you add all this up, the wavelength of the highest energy cosmic rays all the way down to the longest wavelength radio waves, it's 27 orders of magnitude in wavelength that we're now doing with doing astronomy with across these 4 different messengers. So what are those messengers? The ones that we're most interested in are these 4: cosmic rays, gamma rays, neutrinos, and gravitational waves. Here's an illustration again of what might be a large hadron accelerator out in the cosmos. It's producing a beam of matter and radiation, and that includes cosmic rays, hadrons. During propagation, either within or near or even distant from the source, where there are hadrons, there are likely to be gamma rays, and they're especially likely to be neutrinos. The gamma rays can also be produced by other processes, leptonic processes, but if we're interested in the hadrons in particular, then the neutrinos are especially interesting. So we can detect the cosmic rays. The problem is that they travel through intergalactic space and extragalactic space, And they arrive in this direction, for example, after being scrambled by magnetic fields. So if we point back in that direction with a telescope, we're not going to see the source. The gamma rays are undeflected, so that's good, but they can also be produced by all these other leptonic mechanisms. The neutrinos are hard to detect. They have a very small cross-section, but where we see neutrinos, there must be hadronic processes or something exotic like dark matter. And then, of course, gravitational waves are an even newer messenger. So this new idea of building instruments that can detect all of these 4 different messengers can address a lot of exciting contemporary scientific topics, including closely related to time domain and transient astrophysics. And it can help address one of the longstanding questions, which is what are the origins of these hadronic cosmic rays? A little bit of history of multi-messenger astronomy, including neutrinos, is this object. This is the first image of an astronomical object using, in this case, it was MeV scale neutrinos. Who knows what this object is?
The sun.
Georgia. Roger. The sun, yeah.
Sun.
Yeah, this is the sun in neutrinos. So the issue is that, well, one issue, it's very exciting to see the sun in neutrinos, confirming a lot of the physics of how it works. One issue is that the angular resolution is not very good. So this image is actually about 90 degrees across. So that was one milestone early in the history of neutrino astronomy. Supernova 1987A that I mentioned is another one. So here's a summary of where neutrinos come from. So if we imagine the flux of neutrinos in this room, for example, right now, if you hear of cosmic neutrinos, you might think of the cosmic neutrino background from the Big Bang. There are geoneutrinos from radioactivity in the Earth's crust, reactor neutrinos going up in the energy scale, also at the MeV scale, solar neutrinos, supernova neutrinos like 1987A. Then we get to cosmic rays colliding with the atmosphere to produce atmospheric neutrinos at the GeV scale, human-made neutrinos from accelerators also at the GeV scale. And here's the supernova 1987A here for reference. What I'm especially interested in and what I'll focus on is this upper right corner, which is the galactic and extragalactic neutrinos. That's what I call high energy, even higher energy than MeV or GeV, really in the TeV to PeV, 10 to the 12 to 10 to the 15 EV energy range. Now, the nice thing is that we all know that neutrinos travel straight through everything. They're hard to detect. They have a small cross-section. But notice how it's growing substantially with energy. And so a good thing about this high energy range is that the cross-section is substantial. In fact, the Earth becomes opaque above about 100 TeV. So the Earth is actually opaque to neutrinos at this energy range that we're interested in. So that's the good news. The cross-section is growing with energy. The bad news is that the fluxes are dropping with energy. So here are some of those same source classes, but now plotted for flux as a function of energy. So we have the cosmic neutrino background on the left, solar, supernova, reactor, atmospheric neutrinos. And then we have the ones that we're interested in from astrophysical sources in the galaxy and beyond. We need to identify them above this atmospheric background. So one way to do that is that they have higher energy. So we need to look for this excess of high energy sticking out above the atmospheric background. Another technique that I'll point out throughout the talk is that even though at these intermediate energies, even though the atmospheric flux dwarfs the possible astrophysical flux, if we know when or where to look, or if we have hypotheses of when and where to look, we can use that to beat down our atmospheric background substantially. Now, neutrinos are complementary to other messengers, including photons and protons in multiple ways. You can kind of think of them as super X-rays. If X-rays bring us complementary information in medical imaging and so on to visible light, neutrinos are like super X-rays that can travel straight through lots of objects, just not the Earth. But they typically have smaller column densities to deal with when they're traveling out of astrophysical sources. So this phase space is the energy on the vertical axis, the observable distance on the horizontal axis, and some curves that denote regions that are inaccessible to photons or protons. So in blue, these regions at the highest energies at the largest distances are inaccessible because light is actually absorbed by other light, by extragalactic background light. Similarly, at the highest energies and highest distances, protons are also inaccessible to us because they're absorbed by the cosmic microwave background. And so neutrinos, this is sort of the good and the bad of neutrinos. They can come from very large distances and very high energies. That's going to make interpretation more difficult because they might be coming from sources that we don't know exist otherwise, that are not producing photons, for example, and that we don't have any way of cross-correlating with other known object catalogs, but they're certainly providing new information. So the instrument I work on is called the IceCube Neutrino Observatory. It's a cubic kilometer of ice at the South Pole. It's constructed by simply drilling holes 2.5 kilometers deep and repeating that 86 times. I helped build it during grad school. I was fortunate to go on 3 trips down and help install these strings of instrumentation down into the ice. When a neutrino collides with the ice, it makes charged particles, and those make a flash of Cherenkov light. We record those in this array of 5,000 sensors. Each sensor consists of a photomultiplier tube combined with electronics to power it and to read it out. Here's what construction looked like. It's a pretty simple principle for how you drill these holes. Instead of using mechanical means, you just shoot hot water at as high temperature and high pressure as possible. And you keep doing that for a day all the way down and then another day back up. And you end up with a long, very straight, very narrow hole. Here's an illustration of that process. The top layer, the top about 50 meters, is a layer of snow called the fern. And so you use this more like hot butter approach to melt through that. And then you go in with the hot water drill. Just squirt hot water at high pressure and high temperature. It just hangs plumb, so you don't need to worry about it being straight. It'll be straight within a meter, even over the 2.5 kilometer depth. And then if you pull the drill back up, you install, for scale, each of these buildings is the size of a small house. After you pull the drill back up, you install the string of sensors down. And my job during construction was to help install those sensors. So it was a lot of time standing over the hole, and there's a cold updraft coming. You can see the standing water column about 50 meters down. That's where the water pools. Before it becomes, above that, it's more like snow. Below that, it's more like fully densified ice. And it's a pretty spooky thing to stand over that. It's 60 centimeters. When you're standing over it, you realize that's slightly wider than your shoulders. And it's a long way down, 2.5 kilometers. So IceCube has a really broad science portfolio, really interdisciplinary science. For earth sciences, we use properties of the ice that our detector is built in to do glaciology, competitive neutrino physics for oscillation measurements, for example, fundamental physics and dark matter, exotic searches for monopoles and strangelets, and so on. I'll focus for today on astrophysics, on doing astrophysics using neutrinos. What do our signals look like? When a neutrino collides with the ice, if it's a muon flavored neutrino, it converts into a muon. And that muon is now a charged particle that's a long straight track through the detector. So this event display is color coded from early in time is red to late in time is blue or purple. And the size of each dot is the amount of charge received by that PMT. So it's simple to reconstruct the direction of the muon and therefore the neutrino because of this long straight lever arm. We also have other interaction types where cascades can be produced from the electron neutrino flavor, for example. That's a really nice calorimetric channel because basically all of the energy is deposited within the detector as opposed to the muon track channel. We also have a capability of tau neutrinos. If a new tau produces a tau, it has a short lifetime, but it can still travel a macroscopic distance in the detector and then make a secondary shower. So if we detect 2 showers nearby one another, we have flavor identification. And so unlike other telescopes, we have direction reconstruction and also energy reconstruction, but we also have some flavor identification. So that's a third observable that's useful for neutrinos. Our direction reconstruction is about ½ degree for the track signature and about 5 to 10 degrees for the cascade signature. How do we separate our signals from our backgrounds? I mentioned that there are a lot of these atmospheric neutrinos that are always traveling through us and through our detector. So a cosmic ray hits the atmosphere, produces pions. The pions decay into muons and neutrinos that reach ground level and even below ground level. And so there's this rate of muons, atmospheric muons and atmospheric neutrinos that has to be rejected as much as possible. Here are the rates that we're dealing with. At trigger level, we record almost 100 billion muons per year. There's actually interesting science we can do with those atmospheric muons. A small fraction of that, 1 in a million, is atmospheric neutrinos. There's also interesting science we can do with that, including oscillation measurements. And then there's the astrophysical neutrinos that I'm focusing on for today. That's about 1 in a billion. So we're basically looking for a haystack, a needle in a haystack in a sea of haystacks. To quantify that a little bit, here are those numbers again in terms of rates per year. 70 billion atmospheric muons per year, 80,000 atmospheric neutrinos per year. And depending on the energy threshold that you apply, a dozen or up to 100 if you lower the energy threshold, or even more, astrophysical neutrinos compared to those atmospheric neutrinos and muons. One way to identify the astrophysical neutrinos and pick them out from background is using the energy distribution. Here you can see that steeply falling atmospheric spectrum compared to the astrophysical, one model astrophysical spectrum that we're looking for. We can also use the angular distribution. The Earth absorbs the muons. So if we're buried 2.5 kilometers deep at the South Pole and we look up at the southern sky, then we see this flood of muons. But if we look down through the Earth, we can see neutrinos. Now that's going to be a mixture of atmospheric and astrophysical neutrinos, but at least we can beat down the atmospheric muons by looking at upgoing events from the northern sky traveling through the Earth, using the Earth as a filter. Now there's another interesting technique we can use, which is called the self-veto. It was actually after IceCube was constructed that some people realized that not only can you look for events that start inside the detector. If it starts inside the detector, it's not a muon. It's not an atmospheric muon. But if it starts inside the detector, then it has to be a neutrino. The challenge is then, is it an atmospheric or an astrophysical neutrino? It turns out that atmospheric neutrinos above a certain energy are accompanied by atmospheric muons. So if you require a starting event, you can veto not only atmospheric muons, but also atmospheric neutrinos. So that was a powerful technique that led to some of our first interesting astrophysical events. We detected these cascade type events basically as soon as we turned on the detector with the full, with construction complete. So once we had a full cubic kilometer up and running, analyzed the full year of data, we saw 2 events like this that basically light up the entire detector. So that's 1,000 TeV of energy deposited from a single neutrino event. We then used this self-veto technique to reduce the atmospheric background and lower our energy threshold. And then we found another few dozen of these high energy events that are astrophysical candidates. And so that was now above the 5 sigma significance level. And so that was the discovery of an astrophysical neutrino flux, which is at the TeV to PeV energy range. As far as we know, it's isotropic, it's diffuse, it's equal flavor, and it's a steeply falling power law spectrum, but not as steep as the atmospheric spectrum. It's hard to get a sense of scale of these PeV scale events a kilometer across. So here's one of them superimposed on my campus, UW-Madison. So that's what a cubic kilometer of energy deposition in ice looks like floating above the city of Madison. 1,000 TeV of energy. So where are these neutrinos coming from? The next question after you've measured the energy spectrum is to look at their directions and see if there's any obvious source in the directions of the neutrinos. Here are the directions plotted as a function of energy. So the vertical axis is the sign of the declination. The horizontal axis is the energy deposited in the detector. And you can see the number of events is falling off with energy. There were fewer high energy than low energy, as you expect for a steeply falling power law spectrum. There's also some interesting up-down asymmetry. And we can actually see the Earth absorption here. So at the highest energies, we only detect events from the southern sky, not from the northern sky. So at low energies, we can use the Earth as a filter and we can look in the northern sky, but at high energies, the neutrinos actually don't make it all the way through the Earth. That's that Earth opacity that I was mentioning at the highest energies. Plotting them in 2D to look for correlations with known astrophysical objects on the sky. Here's the map that we get. Again, you can see the deficit of events from the northern hemisphere. This is in equatorial celestial coordinates. The galactic plane is running through here. And you can see right away that it looks roughly isotropic. So it's probably extragalactic rather than galactic. If it were galactic, it would have some strong correlation with the galactic plane. So right away, we can see that this diffuse glow is consistent with being extragalactic. It's consistent with being isotropic. If it has a galactic component, it must be small. And also, it's not highly clustered. So it is isotropic. It's not like there are only a handful of sources producing a bunch of these neutrinos. Either it's a truly diffuse, intrinsically diffuse process, or there's a very large number of sources, each one producing perhaps on average less than one neutrino. So that was the self-veto technique that I mentioned. That was the first discovery and measurement of this diffuse astrophysical neutrino signal. The next technique that we used, which is now a different interaction channel and a different analysis technique, is using this idea of the Earth as a filter. So instead of looking, well, we look especially at the northern sky. So that way we filter out all atmospheric muons, and we detect only neutrinos. They could be a mixture of astrophysical and atmospheric. And we look at their spectrum. And this is the latest measurement using that technique. In the bright orange color is the measured spectrum of this diffuse, roughly isotropic astrophysical neutrino signal. In dotted line is the atmospheric signal. And you can see this finger sticking out above it, kind of like the cartoon that I showed a few minutes ago. So we do see this excess of astrophysical neutrinos sticking out above the background. You can also try fitting different shapes to it, but you can see it's still a fairly crude measurement in terms of both the normalization and the shape of the signal. And so one of the big questions is it consistent with being isotropic, or is there maybe a galactic component as well? Are there some important sources that it's not purely isotropic? Is it equal flavor or not? And what's the shape of the spectrum? Does it have some curvature? Is it just a power law across multiple orders of magnitude and energy? And those are things that we're improving. We're improving, continuously improving the precision of those constraints. Zooming out a bit and comparing to other messengers, here's the neutrinos, where you can see again how crude this measurement is so far. We know, we basically know the normalization, the shape of the spectrum, but we don't know them very precisely compared to our sister messengers, which are cosmic rays at the high energies and gamma rays at the low energies. So gamma rays, the diffuse measurement made by the Fermi-LAT is shown in yellow on the left. The diffuse measurement made by Auger of cosmic rays is shown on the right. And on this energy scaled flux axis in the vertical scale as a function of energy, you notice that the energy in each of these messengers is comparable to one another. So that means that the flux is comparable locally. It also means that the local energy density in these objects is comparable. So that's probably not a coincidence. There's probably some connection among these different messengers, maybe some common sources, some common production mechanisms. So there's probably some deep connection between them. However, if you look at a map of the sky, either in cosmic rays or in gamma rays, it does not look like the neutrino sky. So whatever is producing, so if we look at the gammas, for example, if you look at a map of the universe in gamma rays in either the GeV band or the TeV band, it's dominated by active galactic nuclei that are blazars, that have their jets pointed right at us. And when we look at neutrinos, there's no strong correlation between those gamma ray blazars and the neutrinos. So there seems to be some connection between these messengers, but not a simple one. So let's pause there, and it's time for some audience participation. So what do you think is producing these neutrinos? Yeah.
This is more of a question.
Okay.
If you imagine the neutrinos are being produced by some sources, what does it mean that you see in this?
Yeah. So if you couldn't hear, the question is, if the signal looks isotropic and yet we think it's being produced by sources, why is it isotropic, basically?
Yeah, is that something you would expect?
We didn't really know what to expect. It could have been that there's 3 or 4 bright sources and they're making all of it, and we just see them. What it means is that either there's an intrinsically diffuse process that's producing it, or that there's a very large number of, there's a large number of dim sources, basically. So maybe on average, each one only produces 1 neutrino. And maybe it's a really distant population. So what What do people think the sources are? Yeah.
This is a wild thought. I don't know if this is possible, but could you know, cosmic neutrino background neutrinos be scattered to high energies by even higher energy objects, and then sent here? Because if I think it's like a diffuse source, I mean that's a pretty an isotropic source. Is that physically possible?
It's a fun idea. You'd need really high energy in that primary particle. But there were theories along those lines, so-called top-down models, especially like around 2000. I think it's not totally crazy, but then the question becomes, what's that very high energy primary particle? Other ideas?
I'd say some are AGN.
Some are AGN. Good bet. So if the gamma ray sky is mostly AGN, then probably at least some of these are AGN. Others? Yeah, Jack?
Neutron star mergers.
Neutron star mergers. Okay, some of those players that I introduced early on. Neutron star mergers. Others?
Sure. It's a big tree.
There could be some background, sure. I didn't mention it, but we can quantify, we can estimate what fraction of those 100 that I showed on the map are atmospheric. And we think maybe half of them are. So that's a constant background that we need to make sure we're quantifying correctly. Other ideas? Yeah.
Black holes.
Creation of black holes. Yeah, maybe either mergers of black holes or the birth of a black hole, maybe in a gamma ray burst, for example. So yeah, it probably has something to do with these extreme objects that I introduced early on, either the birth or death of stars, including the birth or merger of neutron stars and black holes, or black holes powering galaxies. Others? All right, here's my list. Gamma ray bursts, star-forming galaxies. These are basically normal galaxies that have, like the Milky Way, that have a high rate of star formation and therefore of cosmic ray acceleration. AGN, like Roger said. Galaxy clusters, maybe. Supernovae. Galactic diffuse emission. We know there's diffuse emission from the galaxy in gamma rays. There should be also in neutrinos. There might be galactic sources. We've talked mostly about extragalactic. Maybe that nova that I mentioned at the beginning. Mergers of black holes or neutron stars. Yeah, the nova. Tidal disruption events, maybe. Fast radio bursts. And then exotic theories like dark matter, or who knows, that energetic particle colliding with cosmic neutrino background. So the analysis methods that we do are basically, we take a list like this, we take a source class, and then we cross-correlate between our neutrino directions, which includes some background that we have to account for, and these candidate source directions. If they're coincident in space, that obviously makes the challenge of rejecting background easier. If they're also coincident in time, that makes it even easier. The harder thing to do that's also complementary and important is just looking for clustering in the neutrino data alone. Because maybe, like I said, maybe the neutrino sources are just really far away and they don't have any counterpart in any other known messenger. So to do that, we search for clustering of the neutrino signal by itself. So here's our 10-year data set recently published. This is, instead of point plotting just a scatter plot of all the directions, we calculate a clustering metric, a likelihood. And then our instrument response is pretty different in the north and south. And so we calculate the hottest spot in both the north and the south. Those are circled here. And we take the log of our p-value as the local color scale here that we're plotting in this likelihood analysis. And you can see here that in this image that it's already pretty isotropic. The difference between north and south is from different background rates and instrument response to signal. And so we don't see any very strong clustering. So we know that if there are sources, there are a lot of dim ones rather than a few bright ones. It's roughly isotropic. And we can quantify, at every point in the sky, we can now quantify an upper limit on the flux of a point source in that direction. We can then compare that to the total flux or total diffuse flux that we've measured and just take the ratio between those, and you can calculate how many sources there must be. So there must be at least 100 sources, actually like a few hundred. And so we know right away that there are at least a few hundred sources out there, and there could be many more. Zooming in on that northern sky hotspot, this is an active galactic nucleus known as NGC 1068. it happens to be, so I should mention, in addition to just looking at clustering on the whole sky, we also compiled a catalog of 110 gamma ray sources, and we looked at those particular directions as well. The hottest spot on the entire sky was also the same as the hottest catalog spot, which is coincident with this AGN called NGC 1068, which is a pretty famous nearby AGN. So it might be interesting if that's an actual source of neutrinos. A little bit more about this analysis. Here's that upper limit that I mentioned. We can quantify the upper limit at every point on the sky. It varies with declination. So here's the shape of that curve. Depending on this energy shape that we assume, whether it's either -3 in blue or either -2 in orange. And you can see bands here for where we'd set an upper limit versus make a discovery. And then we also determine upper limits for this list of 110 objects. Those are the crosses. And we also do a population search. So we search for not only individual bright directions, but we also search for an excess of individual warm directions. And we do a statistical search for an excess of a kind of a medium number of warm directions on the sky. When we did that, and then we Charles corrected it. When we did that, we got a 3.3 sigma significance for a combination of 4 sources. So basically 4 somewhat warm sources. And these are what they are. So this blazar that I mentioned early on, TXS 0506, NGC 1068 as well, that one that I just mentioned, and a couple other blazars. So this is kind of interesting, 3.3 sigma. I'll elaborate in a minute about this TXS object. If you exclude the TXS object, then you have 2.3 sigma post-trials. If you look at this interesting nearby AGN NGC 1068 alone, that's 2.9 sigma. So in the statistical realm where it's interesting, but not a discovery. I'll mention briefly that we've also searched for, we've done dedicated searches for star-forming galaxies, normal galaxies like the Milky Way, as well as gamma ray bursts, and we have not seen any signal from those, and we have very strong limits on gamma ray bursts because they're well localized and have very short duration. We can beat down our background and set very strong upper limits. So continuing with the time domain, after we detected this diffuse signal and we don't see any strong point sources in the neutrino data alone, the next thing that we did is that instead of taking a year or two to do the analysis to identify these high energy candidates, we figured out how to do that much faster, to do that in only a minute. And so now we can calculate the direction and the energy of each neutrino on the sky within less than a minute. And if it's interesting, if it's high enough energy that we think the probability of being atmospheric background is small, then we can publish it immediately to the public. And so we've been doing that for several years now. 1 minute latency from the time the neutrino collides with the ice until it's published on a public website. We now do that every week or two, every couple of weeks, and we generate about 20 to 30 of these alerts per year. Keep in mind that they do have background in them. So roughly 50% of them are background, but that means 50% are signal. And if you point a telescope in that direction, then maybe you'll find an interesting source of the neutrinos there. So here's a quick video of the first 10 of these. You can see again that they're roughly isotropic with some declination dependence of the instrument. And after we did the first 10, there was one that was especially interesting. We just name it after its date, kind of like gamma ray bursts and gravitational waves. Remember the color scale from early to late, going from red to violet. And so this neutrino was nearly horizontal, but it was coming from slightly below the horizon. It has uncertainty on the sky of only a degree. Its neutrino energy was about 300 TeV. And we announced it on this GCN web server within 43 seconds. After that happened, as happens for a lot of these alerts, telescopes around the world slewed into action, both on the ground and in space. They pointed in that direction. And they identified one of these blazars that happened to be bright in Fermi-Lat data at the time. MAGIC, another telescope that I introduced early on, also pointed in that direction, and it detected TeV emission from this direction for the first time. So this is a good candidate for a multi-messenger source. It's producing GeV and TeV gamma rays, as well as neutrinos. And that was this, the blazar in particular was this TXS 0506 object that I named early on. So that was the object that made this flare of neutrinos and gamma rays. Billions of years ago, the light was traveling across the universe since then. We built IceCube in time that it received the signal, as well as Fermi and Magic. And then we look back in our data after identifying this neutrino. So first we identified this neutrino in coincidence with the GeV and TeV signal. And that had about 3 sigma neutrino gamma coincidence significance. Then we look back in our data and we identified a second flare. This one alone had a 3.5 sigma significance after accounting for trials from a cluster of neutrinos in time and space without any associated gamma ray signal. So those were the 2 different bursts that I mentioned early on. At least 1 neutrino came from this, from the burst mentioned at the top, but then a handful of neutrinos also came from the lower one that were detected. And so there's some, this is underlying how there's some, of course, it's only 3 to 4 sigma significance. If it's real, this is underlying how there's some non-trivial relationship between the neutrinos and the gamma rays. They're really providing different information, which is why we wanted to use them all along. They're complementary, but it also makes interpreting the analysis hard, interpreting the results. Just to tell you a little bit more about these AGN. So as I mentioned, we think that most galaxies today have giant black holes at their centers. And sometimes they're in active states. They're sucking in matter, they're spewing out matter and radiation. Sometimes the Earth happens to be along this line of sight of the jets, and then we call them blazars. If not, they're still active galactic nuclei, they're not just blazars. And as I mentioned, the GeV sky and the TeV sky is lit up by blazars. They're quite dominant. So a natural thing that we can do is cross-correlate the list of GeV and TeV blazars with our IceCube data, with our neutrino directions. And when we do that, we find no correlation. So even though this candidate source, 3 to 4 sigma, was a GeV and TeV source, in general, the IceCube neutrinos seem to not be produced, at least not in a simple way, by gamma ray blazars. So if you assume either, if you take the population of gamma ray blazars and do a stacking analysis of those, looking for neutrinos in that direction, you can constrain that depending on the weighting scheme, that much less than half of the total neutrino signal is coming from gamma ray blazars. We can also look for non-blazar AGNs. If you're looking off axis, then you might still be detecting particle acceleration in the core or in the accretion disk of the AGN. And we did a large stacking analysis using IR and X-ray data for this source class. And the significance of this result is 2.6 sigma. So another level that's interesting, not evidence in this case, definitely not discovery, but an interesting excess. And the normalization of the signal here is shown in blue compared to 2 different analyses of the total diffuse spectrum. So this source actually alone could explain the entire signal. So it could be entirely this type of AGN. It could also be much less than this, of course. It could also be that this 2.6 is a background fluctuation. Now, continuing with the time domain, in addition to generating alerts that other telescopes can follow up and look for signals in the direction of our neutrinos, a great thing about IceCube is that it's viewing the entire sky, both hemispheres all the time with over 99% duty cycle. And so when other telescopes detect interesting phenomena like gamma ray bursts or blazar flares or novae, whatever it is, we can do a quick analysis and see if we see any neutrinos in that direction. And this is a pipeline that's led by my student, Alex Pizzuto. And we basically identify when there are interesting phenomena and run a quick analysis and check if there's any IceCube signal in that direction. Here's the distribution of p-values from that. You can read more about it in this paper. And we don't see any individually significant analyses in this set of fast response analyses, and we don't see any excess in the population either. A couple of examples of analyses that we've run for that. One is that very first player that I introduced in the story early on. That's the gamma ray burst that happened, whose light was emitted 5 billion years ago. And it was detected actually at TeV energy. So one of the first gamma ray bursts that was detected from the ground by TeV sensitive gamma ray instruments, in this case Magic. And basically IceCube is also a TeV instrument, so searching for the complementary neutrino signal to the gamma ray TeV signal. We did not see a signal with this fast response analysis, so we set this upper limit. This happened to be at an unfortunate declination for IceCube in the southern hemisphere where our sensitivity is not great. And there have already been a couple of these, and so there will be more in the future. If it happens to occur at the horizon where our sensitivity is good, we'll have comparable sensitivity and complementary messenger to the TeV gamma ray instruments. Another example is the fast radio burst that happened a billion years ago. We've searched for neutrinos, 3 papers now searching for neutrinos from fast radio bursts, these very fast millisecond scale mysterious transients. There's growing evidence that they're somehow associated with neutron stars. In fact, there was really exciting evidence just a couple years ago that this is one of the galactic phenomena that I mentioned. So a very similar fast blip of radio emission, but it happened within our galaxy rather than only 30,000 light years away rather than a billion light years away. It was tied to a magnetar, a soft gamma ray repeater, and we also ran this fast analysis to search for neutrinos in that direction. Again, we did not see any, but we set strong constraints. Gravitational wave sources are especially exciting. The graph on the left shows the cumulative number of gravitational wave signals that have been identified through LIGO Virgo observing runs 01, 02, and 03. During 03, we had this real-time pipeline up and running, and we spun off a version of it that was, or in parallel developed a version of it that was especially developed for gravitational wave follow-up. This was led by another student of mine, Ramis Hussain, and every time there was a LIGO Virgo candidate gravitational wave announced, we had our automated pipeline that would search the localization region of the sky map for IceCube coincidences in the same direction. And we got phone calls in the middle of the night, and we'd log in and check if there was anything interesting. Because we're all sky all the time, we could then search for the sky map from LIGO Virgo, identify if there are any coincidences. A real coincidence would be a major discovery that gravitational wave sources are also neutrino sources. Even short of that, if it's marginal significance, we still want to publish it immediately because our localization is about 3 orders of magnitude smaller sky area than gravitational waves. And so we can tell telescopes there might be something interesting in this direction. It's worth spending some telescope time on that direction. So we did that in real time. Typically within minutes or hours, we announced either our upper limits or our coincidence neutrinos for these gravitational waves during 03. Had a detection. We had a couple of 1% p-values per event, but we've run the analysis 60 times now. So after trials correcting, nothing significant. But we do want to have, a sub-discovery threshold so that we can announce these in real time, even if it's marginally interesting. In case, if you also then discover an optical counterpart in that direction, then that raises the joint significance. This one was one of our most significant, the one I showed, with that neutrino directly overlapping the GW localization. That was about a 1% p-value. A great thing about gravitational waves is that from the waveform alone, unlike most other astrophysical signals, you can measure from the waveform and its amplitude, the shape and the amplitude, you can measure the distance of the gravitational wave. That means that you can get energy or luminosity. That's unlike a lot of other things in astrophysics where there's degeneracy between distance and luminosity or bolometric energy. And so this is combining the different messengers for gravitational wave detections and searches. Energy, total bolometric energy emitted isotropic equivalent by the source as a function of distance to the source measured from the gravitational waves. The crosses at the top are the total progenitor system rest mass of the 2 compact objects. The gray plus marks are the total radiated energy, mostly in gravitational waves. Way down here is the GRB signal that was detected from the binary neutron stars that merged. That was one of the early objects I mentioned. Intermediate between them, so we don't have the sensitivity of the gamma ray instruments, but intermediate between them are all these upper limits from IceCube. So now we can set these upper limits on the energy that was emitted in neutrinos. And within this energy band in neutrinos, it's actually lower upper limits than the measurements of the total radiated energy from the gravitational wave signal. We're also searching for a diffuse signal in the galaxy. You can see the model predictions are in the gray band and the purple color here compared to our upper limits. Our upper limits are well below our total signal. So that underlines that if there is a galactic signal, it's at most 10 to 20% of our total signal. And we think there should be a galactic signal. So new methods and new data will continue to improve these searches. We're statistics limited in most of these searches, so we're working on the future. We have a proposal for IceCube Gen 2, the next generation. Gen 2 is also a penguin, so that's a nice play on words. We want to improve our resolution, our precision determination of this spectrum. There's a lot of science in the shape and the isotropy and the flavor composition of the diffuse signal, even short of resolving it into sources. And of course, we also want to resolve it into sources. A nice way to quantify that is whether there are few bright sources or many dim sources. So this is the luminosity of the sources on the horizontal axis and the number density in the local universe of the sources on the vertical axis. Because we've measured the total diffuse signal, there's a degeneracy between being few bright or many dim. That's represented by the orange band here. And our point source searches constrain the upper limit of that. That's the green band. And as we accumulate data and eventually build Gen 2, we push deeper and deeper into this phase space and reject or detect these individual source classes. The first step towards Gen 2 is an upgrade, which is underway. This is basically a dense infill. We're building 7 new strings, which will improve our lower energy response and also enable precision calibration of the detector for which also has high energy implications. So to conclude, this is our multi-messenger set of windows on the universe. It's a little bit of a cliche to talk about it as windows on the universe, but an artist made this visualization that made it literal. I think these are really beautiful drawings. This is the neutrino window on the left, the gravitational wave window in the center, and the gamma ray or electromagnetic spectrum window on the right. And they really are providing very different and complementary views of the universe, sometimes so complementary that it makes combining and interpreting the joint information interesting and challenging. So neutrino astronomy is now a reality. It's a key component of multi-messenger astrophysics. The total, sometimes called the diffuse astrophysical neutrino signal, has been discovered, and we're increasingly characterizing it with more and more better precision. There's initial evidence of sources that have been identified. We know that there must be hundreds of such sources. We know that from the electromagnetic sky in different wave bands, there's a huge diversity of different sources. So it's probably true in neutrinos as well. There's probably not just one dominant source class, but probably there are a few different ones. And we're working on next generation instruments that will help answer what they are. Thank you.
This upgrade, are you able to run while upgrading? Which I think is sort of an interesting thing to experiment to be able to do.
Yeah, we did during construction. It took 6 or 7 years, and basically the detector just kept growing, but it was an array, and just the volume and the sensitivity kept growing. And so we plan to keep running during construction.
Made a point that for the background gamma rays, neutrinos, and cosmic rays have the same total energy. This coincidence means they're related, but it clearly cannot be hadronic production of neutrinos, because if it was, then neutrino energies should be comparable or smaller than gamma rays in the background. So, but it must be different process producing such high energy.
Yeah, well, we know that the gamma rays have leptonic processes that produce them. So we know the gamma rays are not purely hadronic. So, but the neutrinos have to be either hadronic or something exotic.
Yeah, I'm saying if the total energy is same, why are the individual neutrino and photon energy same?
I'm not sure if I mean, we're talking in order of magnitude sense. So there's definitely room for, you know, only a third of the gamma rays could be hadronic, for example, but they all have comparable order of magnitude.
PP interaction, for example, the neutrino energies are slightly smaller than the photon. Maybe by factor of 2 or 5.
Yeah. So there's, yeah, I think there's room to accommodate that, but it's striking that they all have comparable energy densities. Striking, but somehow not a trivial relationship.
So, I mean, I understand that the ice flows a bit at these large depths. I'm curious, how much has it flown since the first strings went in? And does that actually matter to your reconstruction at all? Does the geometry change around?
Yeah, I forgot who we were talking about that earlier today. So yeah, it flows. It's basically a glacier. It flows about 10 meters per year. There's actually a ceremony on New Year's Day where they move the marker of the official pole every year. And it's basically a rigid body. And then at bedrock, there's a no slip condition. And so the shear happens only in the bottom layers between the bottom of IceCube and the bedrock. And and so there is a very small amount of tilt that we think we've identified in the bottom of the strings. We actually have tilt sensors installed. But also it's not clear if we expect the strings to flow with it or maybe around it. The copper is kind of ductile, but so is the ice is also pretty plastic. So you could also imagine the ice flowing around the strings if needed.
Are you saying that you don't even, it's 10 meters a year, but you don't know if your strings have shifted that amount or not?
Well, so the whole thing is rigidly shifting together. And the models predict that if there is shear, it should be at or below the bottom depth of the strings.
Right, but the question about whether the ice flows around the strings or the strings move with the ice on the surface, presumably you know that it's moved 10 meters a year.
Yeah.
Do you not know that at depth it's come along with the surface? I mean, that would surely distort it dramatically. So you must know that it is basically rigid.
Right. Okay. Yes, that's right. Keep in mind also, the effects we're looking at are, I mean, we know the whole thing has moved rigidly at that level.
You have a way of surveying the the oceanic ones, right, where they have fingers and they.
Yeah, we use just optical flashers. So each DOM has 12 LEDs, and we can just flash in any combination.
The relative position.
Yeah.
Roger.
Yeah, just could you say a little bit more about the prospects of maybe going to higher energies and looking for radio detection of neutrinos? I know before you tried to make it detection, but is there any hope for that? And I guess related to the first part of that, it's the GZK neutrino, which you mentioned. You say, what do you now think of the prospects for all those things?
Yeah. So I got started in this field with Giorgio listening for neutrinos in the ocean. And then even my PhD was on that in IceCube. There's still some people working on the acoustic idea at the highest energies. It's not quite as promising as it was a decade or two ago. Radio is still very promising. So the baseline plan for IceCube Gen 2 is to have a radio component. And that's how you get this very high energy response and to unify it with IceCube. And there are a variety of different radio techniques. The main one that we're focusing on for IceCube Gen 2 is called the Ascarian technique, where you get a radio pulse that's emitted by the neutrino-induced shower inside the ice, and you can use that to detect the very highest energies. And it outperforms the optical Cherenkov methods above 10 to the 17 eV. There's this gap between the radio method and the optical method in the 10 PeV to 100 PeV range, which is especially interesting before you get to the cosmogenic neutrinos, but at the end of what we've measured so far with IceCube. So any techniques that can fill in that gap would be especially welcome. But I think the radio methods are promising for detecting cosmogenic neutrinos.
Just a short one. George and I recently were at a very nice talk on the Glasgow resonance event, and I'm curious, with the upgrade, what are your rate of those going to be, and how many do you expect to get over a decade? Yeah,
here just to fill people in. So So the cross section versus energy is smooth for the most part. There's this resonance where electron antineutrinos collide with atomic electrons, and then you get a W production at resonance. And in terms of the neutrino energy, that comes out to be 6 PeV. So here's the paper where you can read more about this. So we detected 1 in a decade of data. So I think you can scale that by about 5 for a Gen 2. This is using an event selection, which is uncontained events. And so understanding the instrument response to that is difficult. So I think there's work still to do about how that will scale to Gen 2. But this was an event that was not contained. It was outside the detector. And so energy estimation, of course, is also difficult.
So Justin, back on slide 22, you have all these different areas of science addressed by IceCube. How many of those were known before when you proposed the experiment? How many came up when you needed to understand backgrounds, et cetera?
Yeah, that's a good question. When I was a prospective grad student, it came down to Wisconsin or Berkeley, and the Wisconsin people said, "Go to Berkeley if you want to study dirty ice," and that's what I did. And it turns out to be fascinating. So my advisor there, Buford Price, has done a lot of his career doing interdisciplinary science that spun off of challenges in understanding the detectors that were originally built for some other purpose. So the ice is very clear there. It's the clearest naturally occurring large volume solid substance on Earth. That's why we're there. But it does have dust, and that dust scatters our photons. And so understanding that is our dominant systematic. And so we have interesting collaborations with glaciologists to understand not only the dust inside of the ice, but even the crystal structure starts to become relevant to the optical properties. So all of these things are, interesting science that comes out of understanding your systematics. Another example is neutrino oscillations. IceCube was well under construction, nearly done with construction, before I heard people start seriously talking about neutrino oscillation physics, and I thought it was crazy. I thought we'd never get the energy and the resolution that we needed. And now we have world competitive constraints on masses and mixing angles. So I don't know how to put a fraction on it, but a large fraction of these were not thought of at the time IceCube was proposed.
One more question.
Sort of a science adjacent question. You have to explain what you do to a 10-year-old?
Good question. Explain what I do to a 10-year-old. I would say I look for big flashes of light in Antarctica and try to figure out what in the universe made them.
That's a few steps to be Okay, well, with this, I think we should thank Justin again. And we have food by Varian Purple Beach.
Thank you.
But I was puzzled when if the neutrino background is hadronic, then there should be same